Welcome. If you're new to this webinar series, my name is Dr. Chris Murphy. I'm an admissions tutor and a plasma physicist in the School of Physics, Engineering, Technology at the University of York. Welcome. So about the series, this webinar series will bring you cutting-edge research from the School of Physics, Engineering and Technology at the University of York to give you a glimpse at some of the range of exciting areas that our engineers and physicists are working on. You can keep up to date with our upcoming lectures on our webpage, and you can watch previous webinars on our YouTube channel. You'll find those links in the resources tab on your screen. They should be being posted now as past events on that resources tab. So now to tonight's event. Since the 1960s, we've launched lots of things into orbit, many of which are still up there. This is problematic for lots of reasons, including to astronauts or even for communications that we use every day. To help fix this, new robotic technologies are being created. Some of these solutions include modular satellites that can be assembled and serviced in orbit, an autonomous network of robots who will do the maintenance in orbit without the risk to our astronauts. So we're going to explore some of these cutting-edge research development being done right now on projects such as the robotic space warehouse STARFAB that will define new ways of using and working in outer space. Our speaker tonight is Dr. Mark Post. He received his Master's and PhD in Space Engineering from York University, but not this one, the one in Canada, and is currently a senior lecturer here back in Intelligence Systems and Robotics at the University of York in the UK. His research focuses on adaptable autonomous robots and cyber-physical systems for space and other challenging and distant environments. He's created autonomous agricultural mapping systems, sensor fusion, and control algorithms for orbital and planetary vehicles, tensegrity and bio-inspired land and underwater robots, and communicating modules capable of knowledge-based self-reconfiguration. Basically, that robots who can look after themselves. So it's my great pleasure to be able to introduce Dr. Mark Post, and he'll take it away with his presentation for this evening.
Thank you very much, Chris. So welcome to the webinar. My name is Mark Post, and today I want to talk a little bit about what we need to do and what we have been doing to try to fix the mess we've created in space. So sending up things into orbit has been something that we've been doing for ever since the 1950s. So the problem is, of course, when we send things up, they don't come back down. So we've been dumping our trash, essentially, into space since 1957, when we sent up Sputnik and the Vanguard satellite, the initial satellites that started out the whole process. And over the years, 1980s, 1990s, we've accumulated over 10,000 active satellites, 13,000, including non-functioning satellites, that is ones that don't work anymore. We've got 60,000 objects that are trackable in orbit, 500,000 that are only 1 to 10 centimeters of size, and 100 million actually up there that are untrackable. And these are all bits and pieces of technology up there that we haven't been able to see since they've been launched. So these can be very dangerous. You have tiny, tiny little fragments of technology up there traveling it around at 10 kilometers per second on average, some of them faster, some of them slower. At that speed, these tiny little objects can cause huge amounts of damage. You have Space Shuttle window example here. This is from a paint fleck. This big crater on the top left is actually just from a tiny, tiny paint fleck this size. You can see that Hubble Space Telescope has had holes knocked in its solar arrays over time. You can see this hole on the Canadarm2 that was caused by a very small sub-centimeter piece of debris. And you can actually see the moment on the bottom right that an impact occurred on the Sentinel-1A satellite that's caused a 40 centimeter size hole, essentially, in the side of the satellite. And these are just tiny things. Now, what happens if they scale up? What happens if you're talking about big satellites here? And it happens in 2009, 2 satellites did collide. The first unexpected, uncontrollable collision of 2 satellites, Iridium-33 and the Cosmos 2251. They hit, just as you see there, they created 3,000 and more tiny pieces of debris, which circled the Earth around the other side And they once they've circled the Earth, the problem is they will probably hit again, just like you see here. And as a result, you get this sort of ecosystem evolving of space debris. You get debris that collides and more debris is produced. And there's been simulations of collisions with larger satellites, such as the Loft satellite over here, where you see a very small satellite hitting a large one, and it basically fragments it into tiny little pieces. All these pieces, some of them shoot down to Earth, some of them go up, some of them just stay in orbit. And if you look at the number of disasters and near disasters that have been caused, there's a big list. There have been, for example, residual propellant explosions from rocket bodies. This has added almost a million 1 centimeter and up sized objects. This is ever since 1961. In January 2007, the Chinese conducted an anti-satellite missile test, which unfortunately added another 25% to the debris that was already up there. Iridium collided in 2009. The Russians actually did an anti-satellite mission test in November 2021, but fortunately they did it low enough down close to Earth so that most of the debris burned up in the atmosphere. But some of them are still up there. And then we've had a series of near misses recently. 2023, we had a space telescope come within 15, 30 meters or so of a inoperable satellite. We had an unmaneuverable NASA satellite, the timed satellite, that would almost hit another Russian satellite, Cosmos 2221. And then you have situations where debris falls down to Earth. You have cargo from the ISS that was actually documented to fall all the way down to Earth, survive re-entry, and hit someone's house and made a big hole all the way from their ceiling down to their floor. And we don't want this to happen, of course. We maneuver our satellites out of the way of potential debris collisions. We're very, very careful to ensure that satellites don't run into things. So we have, for example, SpaceX's Starlink constellation, which is thousands of satellites. And these satellites are maneuvering constantly. In fact, in 2025, they had to maneuver every couple of minutes just to keep from adding to the space junk, to keep from colliding. And now we have the International Space Station, which is going to be deorbited in about 2030. And we have to make sure it comes down and doesn't hit anybody. So that's going to be a big problem. And the important thing to remember about all of these collisions and near misses, they're all preventable. They're all things we can somehow work around if we're capable, if we don't do anything dangerous or silly. Now, the problem that is created by all of these, pieces of junk up there is often described as the Kessler syndrome. This is a word that was coined, it was named for astrophysicist Donald Kessler, who started raising alarms about this idea of space junk colliding with other space junk and causing these huge, increases in debris around the Earth back in 1976. And that he wasn't very popular. Nobody wanted to hear about their satellites causing these huge environmental disasters, down the road. But it turns out it was something that they needed to start worrying about because as debris flies through space, the more of it there is, the more likely it is it will collide with something. The more likely that collision will produce more debris, smaller debris, pieces of debris, essentially. You can characterize this basically as in terms of mass per cubic kilometer. The more mass there is, the more pieces of debris per kilometer up there, the more likely stuff will collide. And you can see it from the graph on the right here. The number of objects in Earth orbit has been going up and up over time, ever since the first satellites in the 1950s. You see huge increases. You see over in, for example, 2007 on this graph, there's a big jump. That's the Chinese anti-satellite missile test. You see another jump in 2009. That's the Cosmos Iridium collision. And you also see the fragmentation debris, the pink line, actually goes down a little bit over 2010, 2011. That's actually debris falling back to Earth, that stuff burning up in the atmosphere, because we're not adding as much. They were starting to get a little bit smarter then. They were starting to actually produce a little bit less debris on average. But the problem is it's not going to go away. It's still there. And with the number of objects we have in orbit, it's no longer a matter of if they will collide. It's just a matter of when. The longer we wait, the more collisions will occur. That's the way it is. Now, this may sound awfully, negative and kind of like, there's no chance of recovery. It is true in low Earth orbit, there are some places like the Iridium constellation area where we've actually got so much space junk that it's going to keep increasing if we do nothing. If we don't put anything else there, it's going to increase. We're past the tipping point. But maybe this doesn't tell the whole story. It's true, actually, that we haven't completed all the research on space junk. We haven't explored every option. Some professors, such as Morab Jah, who I've met in person, who's a very clever person and understands the situation, have suggested that instead there is a sort of orbital carrying capacity. There's a number of pieces of debris that we can manage in orbit without things going horribly awry. So we will need to do more work on it, but in the meantime, we need to do something about this. And the question is, what should we do about it? Well, the late fix, I would say, the end of pipe solution, in a sense, is to try to take down some of that junk, try to remove things from orbit. And that's what we're trying to do right now. What do we need? I really like this illustration. This was actually by a boy named Brandon Selly, who did an illustration for the Globe and Mail many years ago. And we really need a space garbage truck, don't we? Something that can go up there, grab all this stuff, put it away, drag it down to Earth. It sounds simple. Problem is, everything's really far apart. It's not all together like this. It's not all in one place. It's really farly spread apart, and it's traveling at huge speeds. So we can't just grab it necessarily. Maybe some of the big ones we can grab. ESA, European Space Agency, of course, has been working very hard on this. And they developed a couple of studies. They developed the Service-Oriented Active Debris Removal study and the ED-Orbit mission. And the idea behind ED-Orbit is you go up there and you try to get some of these big pieces of debris, these rocket bodies, these satellites, the ones that are causing the biggest risk of collision that are sitting up there. This was back in 2016. They recognized that these big pieces produce the most debris. They're the biggest cause of concern for being able to remove space debris. So what they're proposing is, in order to counter the increasing number of launches of new satellites, they want to put up robots that can drag these satellites that are end of life out of orbit and get them out of the way. And it's like a tugboat, basically. The idea is that you would go in with a satellite with a robotic arm, a space robot of a sort. You would grab a dead satellite. The satellite is not able to move. It's not able to deorbit, but you'd pull it out of orbit using the space tug. And it's a very, very difficult thing to do, because if you try to grab something in orbit and you mess it up, you either create more space junk or you push it away in a different orbit. So synchronizing with that target is very, very important. And grabbing it is very, very delicate. It's extremely difficult to do, especially since there's no humans up there to joystick it for you. This all has to be done robotically, autonomously, and ideally. Another option is you can send a net out like this. You can fire a net, you can grab the object, and then you can drag it down. And these are probably the safest ways of being able to clear out space a bit, just like this. Now, the question is, have they actually done this? Well, as a matter of fact, they have done controlled tests of these technologies. So in 2019, they had the Remove Debris mission, which basically tested out a net, as you see on the top left, and actually managed to capture a simple target that was put up there just to be captured. Not a piece of space junk, but a target that was for testing. They also developed a harpoon. Astrium, in fact, developed the concept for the harpoon, and they tested it in. Think of a harpoon as a space junk type tool, but as a matter of fact, it's designed to hit a target, to grab onto it, lock onto it, and to be able to pull it out of orbit. So here's a picture of the harpoon firing. And this is slow motion. This is 1/10 of its normal speed. So it actually moves very quickly. And you can see it hits that object and it embeds itself in the object. And, ideally, if nothing goes wrong, if the object doesn't fragment into tiny little pieces or go flying back down to Earth, ideally you will end up with this. You'll end up with the object nicely tangled and grabbed so that you can drag it out of orbit. And we always worry about this a little bit because maybe that satellite will blow into pieces. I always think about it a little bit like Moby Dick, harpooning a satellite like a giant whale and then dragging it in. But the problem is we haven't gotten to the point of actually dragging real space junk out of orbit. So here's a timeline of what we've done. We've done, since 1987, there have been some experiments in mitigating space junk, grabbing things in orbit, dragging them out of orbit. There's a huge number of examples. NASA has figured prominently in these, but also ESA and some private corporations. But the closest we've come actually to getting real space junk and starting to make a difference is the Clear Space One mission, which follows along from ED orbit, which follows along from the initial Phase 0 study, as I've indicated here. And this has been such a series of setbacks, of delays, really, that originally we were supposed to do Clear Space One this year. It was then delayed until next year. Now it's delayed until 2029. So we're all a little bit worried about when this is actually going to be happening. We hope that it will happen soon, certainly. The sooner the better, before things get worse. Is this the only way of dealing with these things? What about those tiny little pieces that we can't track easily or that we can't grab with a robot arm? Well, maybe everything's better with lasers. The very best methodology I've seen, really, for being able to deal with small space junk is to use big projectors, laser projectors, I should say. Sorry, let me restart that. To be able to use giant lasers that are Earth-based or potentially based on orbit to shoot these tiny little pieces of debris that you see there. And the purpose is not to destroy them completely, but with that beam of light from a laser station, you can change its orbit. You can move it, push it out, push it up, or push it into a different orbit when it will actually burn up in the atmosphere. So you have to track these things really accurately. You shine a laser on them for a period of time, and that laser will eventually change the orbit enough so that they will change orbit and they won't hit anything. And this is, the initial testing indicates it's possible, but again, we haven't gotten to the point of actually being able to shoot things out of orbit. You can also use them as a network, which is also kind of handy. You can use them for communications. But this research is still ongoing. So we have a lot of problems to deal with. I don't think we're going to be able to get enough garbage trucks up in orbit to cover the 200 billion kilometers or so in low Earth orbit, much less the orbits higher than that. Active deorbiting technology is still being worked on. It's still underway, being developed, being tested. And if we don't get it right, if we somehow mess up and hit the satellite too hard or knock it into a different orbit, it'll just make the space junk problem worse. So we only get one shot when we're trying to clean up space junk. Even if we get the large debris, there's a lot of small debris that we can't even track. We don't really have a solution for that yet. We don't have a way of dragging a net through space to get rid of all those tiny little pieces that can cause huge amounts of damage. So really, and if the longer we wait, the longer we fix these problems, the less fuel the existing satellites will have to avoid space debris. And if they run out of fuel, they become space debris themselves. We also have space law to deal with. We don't really know these days who owns all of that debris. We can make a guess, but a lot of it we don't know. You know who owns it. You might ask the person who's put it up space a permission to remove it. That's the way space law currently works. We can't just pull out someone else's garbage without their permission. So many things need to be overcome at this point. Many things are still being improved upon, I think, and developed. In the meantime, we do have something we can do, and the thing that we can do is just don't pollute. The best way to prevent this problem from getting worse is to develop a space ecosystem by which we don't put junk into space as much as we possibly can. How do we do that? Well, the work that I'm working on and the work that's currently very popular in European Space Agency and elsewhere is to build modular spacecraft. Currently, spacecraft that you send up are very much like NVSat-1, which is shown on the top right, gigantic school bus-sized weather satellite. It's been up there for decades. NVSat-1, we can't deorbit it right now. We don't have a robot powerful enough to pull it out of orbit, literally. So all we can do is dodge it. But what if we broke the spacecraft up into separate modules? What if its hardware was not a single piece, but if it was actually small modules? So instead of these monolithic single-use spacecraft that are very expensive to build, expensive to launch, and difficult to deorbit, let's build something that can be maintained. We can't allow satellites to become non-functional, so we have to build them out of multiple pieces and ensure that at least some of those pieces can keep working all the time. Make sure that they're resilient. If we send only the components needed for a spacecraft or robot, we can save ourselves a lot of money. It will be much easier, much cheaper if we send up only the components we need instead of sending up a whole satellite every single time we need a piece of instrumentation in orbit. And then we can assemble satellites on orbit. We can assemble modular components into satellites using robots. We don't need humans to be there. Very much like the image on the bottom right, we could have some sort of a service station in orbit that works with a network of robots and spacecraft to repair satellites, to reuse satellites, and to be able to work with the different components to ensure that those satellites keep working. To do this, we can't just keep going the way we have. We need to rethink how we engineer robots, how we engineer satellites, how we engineer systems. So let's start rethinking. Let's think about what we can do to build systems that are a little more organic, systems that are, that can evolve, can be serviced, can be fixed, can be improved in orbit. Let's take a hint from nature. Humans themselves, and all animals really, are modular systems. We're all made up of cells. And all of these cells, they're built one at a time, separately. You don't build the whole system at once, just like you don't want to have to build a whole satellite in orbit potentially at once. All organisms in nature evolved from symbiotic cells that are kind of like our components. They're kind of the things that we can put together in order to make organisms with. The cells are different. They're not all the same. They all do different functions. They communicate with each other as a whole. And you get many benefits from this. For example, you can reorganize those cells to improve performance. You can give them a general directive. You could give a satellite a general directive, say, observe Earth with 3 or 4 cameras at once, and it will be able to organize itself to do that. If you need to change something, you can reconfigure. You've got satellites, for example, that are old, that are running out of fuel, that have low batteries, that need new components. We want to be able to change those out, add new cells, add new functionality to them, and make them modern again, make them usable. And if things fail, we want to have redundancy. Cellular organisms have lots of redundancy. You can lose a few cells and they keep operating. Modular satellites, you lose a few modules, you lose some functionality, at least the satellite will keep operating. It will be cooperative. You can deorbit it or you can capture it. So yeah, it would be great. We'd like to have modular robots. We'd like to have modular satellites. There's been lots of work in the past on modular robots and modular systems. For example, the modular artificial life that's been done in the lab. robots that can walk, robots that can change their morphology, robots that can be assembled into larger structures, and even a few concepts on the bottom here of space modular robots. But we don't have them yet. And that's the tricky thing. Why don't we have modular robots yet? Well, it comes back to that problem of systems engineering, really, of being able to have a different way to engineer things. There's a few critical things that we don't have in a lot of modern engineering. We look to nature for inspiration about those. We can't build a modular system out of just one kind of cell, one kind of module. We have to have many different kinds. If you have many different kinds of components, they have to communicate somehow. They have to interface. They have to talk the same language. So communications is important. We need to make those things self-aware enough to manage themselves. We can't afford to have a ground crew for every one of those 10,000 satellites in orbit. If they're about to hit a piece of space junk, or if they need servicing and they have to go in for a refueling, that should be done automatically. We need to have that functionality basically automated. And then there's complexity management. If we build these huge, complicated modular systems, it's very difficult to plan out how they would work and how they operate with all those different components. It's hard enough to build a normal satellite, a normal robot. Modular robots can be even more complex. So we need to be able to make them explainable. We need to make them capable of saying, this is what I do. This is what I am. I'm a camera module. I give you images. I'm an actuator module. I move things. And have the systems themselves figure stuff out, figure out how to operate and accomplish your mission goals. So we've been doing some experimentation. We've been building modular systems at York in my lab for quite some time. And we built some experimental systems. So what you see here is our lab experimental modular system. It's kind of a prototype for the way we could build space robots, the way we could build satellites. And the idea is we just use off-the-shelf hardware. We use the Raspberry Pis, the Xilinx Zincs, the NVIDIA Jetsons, all those things you can buy off the shelf. It's okay, it's not going into space just yet. But we can experiment with how these modular systems have to communicate, how they have to interoperate, and how we can make them more self-sufficient so that they can do all of these tasks in space that we don't have to oversee all the time. So hopefully we'll be able to build an ecosystem in space of space components, of modules or cells that will allow you to build whatever satellites you need in the future. The modules, of course, have lots of other uses. We've experimented with how to make them locomote. Maybe we'll be able to put modules like this, our modular tensegrity robots, for example, on another planet someday. Maybe they will do exploration for us. Maybe they will be able to traverse the surface of the planet and walk or crawl. And maybe they will be able to do all of these self-reconfiguration so they can convert themselves into whatever kind of robot is needed. But back to space robotics specifically, and back to what we're doing right now on orbit. The European Space Agency and the various other space contributors, space primes and companies are quite aware of the problems and have been working towards technology that we can use in space to solve the space junk problem. So many years ago, actually, I would say about 2015, 2016, I was involved in several projects funded by Horizon 2020, which was a program that led a lot of research. And some of the research was specifically on creating modular, reusable, and standardized technologies that we can use to build these space robots with. The Perispera activity was founded in 2014, and it created essentially, it funded a set of projects that created building block technologies, these fundamental sorts of modular technologies that we need to send up in all of our space robots and satellites. And this were funded in several operational grants. I'll tell you about a few of them because they were quite interesting. It's important to realize that these technologies were constrained to be specifically interoperable. because with modular systems, you can't have, everybody just going off and developing their own solution. You have to have commonality. You have to have that kind of connection between everything. And we had to build on that technology in subsequent projects to make sure that it actually got used and it got developed and matured so that we can use it in orbit. And so all deliverables also were open sourced, which is great because anybody out there, you and me, can make use of what we developed. The source code, the designs, the documentation, it's all out there. So I encourage you to have a look at some of the projects that we worked on if you're interested. The projects nominally went until about 2019, after which we started working on other things. But the technology is still being developed and used in new projects towards these common modular objectives. So the first thing that we did, we developed modular software. You're probably aware that robots, autonomous systems need to have some kind of software ecosystem by which they can recognize targets, they can do work, they can identify objects. And we developed a bunch of those algorithms. For example, recognition of robots, being able to identify satellites, being able to identify rocks on other planets if you're talking about planetary rovers. And we put all of this into a modular architecture that we called the Common Data Fusion Framework, or CDFF. And this was done in our Infuse project, which started back around 2016. So in Infuse, we developed modular software that we could implement on satellites, on robots. And then we still, of course, had the challenge of interconnection, interoperability again. So another one of those projects called SIRM, the Standard Interface for Robotic Manipulation, developed this standard connector. And the idea is that all of your modules, all of your individual cellular components connect to each other using this connector. And of course, as you're probably aware with engineering, if you get 10 engineers into a room, you'll get 10 different solutions. Well, the same is true of standards. There's so many. The great thing about standards is that there's so many of them, right? So there are, in fact, many standards of robotic interconnects for space now. There's the SIRM, there's IBOS as well, which was developed by DLR even earlier. There's HotDoc, developed by Space Application Services in Belgium. And they don't perfectly operate with each other. It would be nice if they did. However, there is now a project called Space USB. In that project, they're trying to build a single connector that unifies these standards, that allows all of them to interconnect, and that will hopefully, perhaps not solve all the problems immediately, but will certainly lead us down to a path to a day when all of our robotic components can interconnect seamlessly. So that's hoping that will be successful. We also did a project called MOSAR, which was Modular Satellite Assembly and Reconfiguration. And MOSAR was really sort of the culmination of this idea of modular spacecraft. And what we did is we did a demonstration that you see in the video here of spacecraft modules, components that we can assemble into satellites, being assembled by walking manipulators. These manipulators, like this robot here, can actually pick themselves up and walk end over end on a satellite in space. So that being able to assemble things autonomously in space is really key to this kind of space ecosystem where nothing gets disposed of and nothing goes derelict. So we were able to demonstrate that, yes, we can autonomously assemble a satellite. Haven't done it in space yet, but the technology is mostly there. And that led to what we're currently working on now, which is STARFAB. STARFAB, which was mentioned in the introduction, is really a space warehouse and an orbital hub that sort of encapsulates what's called the new space mentality. New space is all about, individual companies and small companies being able to put up their own satellites and participate in having things in orbit. It's about being able to service things in orbit. It's about modularity, interconnectedness, and being able to recycle things and service things in orbit. And to do all of that, you need sort of a focal point. You need a gas station, a service station, if you will, where everything can come together to be able to be serviced and to be upgraded or deorbited and disposed of as need be. And the concept behind StarFab is really that we have uh, a hub that allows us to store these modules that we've developed, so spacecraft components, solar panels, thrusters, fuel tanks, communications antennas, scientific equipment. All of this modular equipment can be stored in a warehouse unit that we can have in Earth orbit, probably low Earth orbit, somewhere where it's close to all the satellites. And we can actually send out servicer spacecraft that will grab the satellites that need to be serviced, just like we described in ED orbit, and we'll bring them back over to the orbital hub. And that orbital hub will take the components off, replace them as needed, service them, possibly even manufacture new components, and then send them out again. And the newly refurbished satellites will not pose a problem. So of course, a system like this, it's heavily robotized, it's heavily automated. It's like lights out manufacturing. So it's going to need a lot of different sensing technologies. And what York is actually contributing to StarFab now is called the Mobile Inspection Module, or MIM, as we call it. So the Mobile Inspection Module is basically an inspection and non-destructive testing robot. The robot's modular. You can see it here with three legs on it, but the legs are actually mobile manipulators. You can detach them, you can reattach them as needed. And it has a sensor array on it. It's an optical sensor array. We can detect defective or damaged objects on orbit. We can inspect modules to ensure that they function correctly. We can inspect StarFab, the whole system, as it were, to see how it's operating and determine whether repairs are needed, make sure that everything is working well, and so on. It's our eyes, essentially, on StarFab in orbit. And a lot of the algorithms are open source. It builds on all of those technologies I talked about earlier, like Infuse, StarFab, and so on, or Infuse and Mozar, and so on. And this is the state we're at right now. So we actually have in the lab, we have a sensor module. You can see it's built out of off-the-shelf components, stuff you can get on Amazon and eBay. So it's just a prototype. It's not something that we're just going to send into space immediately. But we want to use this to verify that, yes, we can do inspection and maintenance automatically, autonomously on StarFab. We want to be able to show that it's reasonable to be able to do satellite assembly, reconfiguration, and storage on orbit, and to be able to improve the robotics technologies to the point where humans don't need to oversee every little thing. And so, yeah, this is a work in progress. StarFab will actually wrap up around June next year, but we're hoping that we will be able to continue the work as we have, and we're hoping that we'll be able to get to the point at which we can start sending up modular components, modular satellites, fully autonomous robots that will take care of our space for us and prevent it from ever getting any more polluted again. So thank you very much. And yeah, I'm happy to take any questions.
That was really interesting. Thanks very much for that, Mark. Learned lots about the problems that we face with the space junk and how your research and others are helping to contribute to the solution to that. What is there going to be something for the ISS going to be launched? I mean, I guess
Okay,
that's
so
the idea.
this is the tricky thing. The International Space Station was an international effort, as most large projects in space really need to be. And the ISS has actually it has shown that we can accomplish putting things in orbit, but it is not the most recent technology. As a matter of fact, if you want to look at the Chinese space station, that's remarkably modern compared to the ISS. And we would like to be able to use more recent technology to replace it. The thing that is missing right now really is money. You're probably aware of the world situation. Many countries are wary of each other right now, which makes international cooperation a little bit more difficult. And also, NASA is, shall we say, experiencing some, legal, some policy difficulties with the government. This has slowed things down quite a bit, and I'm sorry to say that there are plans on the table, but there doesn't seem to be very much action specifically towards replacing the ISS. I think if the different countries can get together, if they can overcome their differences and say, look, this is for the common good of humanity, we need to replace the ISS, and we do need to because it's getting very long in the tooth. I think we will find a way because the technology is there and it's good technology. We've improved immensely.
Yep. I mean, there's a second question here that it kind of touches on that a little bit, but almost, I presume when you're talking about international collaboration for the ISS, you're maybe, well, China's got their own, right? So there's a question here saying how much international cooperation there is there?
Mhm.
And I would say generally, I would ask that
Mm.
question as a general question, but specifically the questioner is asking about with people like Russia, China, North Korea, maybe countries that are not traditionally as friendly to Western countries.
Yeah, I would say that there is still cooperation. Despite, the China situation, I would say that we still have very good relations with researchers there. We have lots of students come over here from China to study. We have regular missions over there to universities, and there is a lot of knowledge exchange over things like space technologies and potential space science and ways that we can solve problems with robotics. Um, there are many new players, I think, over and above, the original sort of group that started the ISS, which is mainly United States and Europe and Russia and Japan. So China is now a big player. India has shown that they can launch as well. They have a space program. They've made great progress. And the individual space agencies in Europe, I would say, from all the different countries, I think they are working together much better than they used to. In fact, I think ESA, as I mentioned with the projects, has made quite a lot of progress towards where we need to be. So it may be not quite the same, not the same conglomerate of countries that originally were space innovators, but certainly, they are still there. And my hope is that everyone can get along in the end, and we can get back to where we were when we put the ISS up.
Excellent. There's a question here. Would using magnets to remove smaller pieces be possible, or would that cause problems with magnetic fields on Earth, or what would a
Oh yes,
magnetic solution be?
absolutely. In the slide that I put up, you may have noticed that we had little rings of magnets around those modules holding them together. Yes, that was a convenience measure. Now, if you put a magnet on a satellite in orbit, the Earth has a pretty big magnetic field. It's not super strong like Jupiter's or anything, but it's strong enough that a magnet will eventually orient itself with the magnetic field. And a satellite that's got a magnet in it will gradually orient itself over. We make use of that, for example, to orient satellites towards the Earth to make sure that they don't change direction if we don't want them to rotate. But most satellites, we want to be able to control them. We want to be able to rotate them. And if you put a magnet on it, basically, you're going to spend a lot of energy trying to rotate it against that magnetic field that you don't necessarily need to.
Yeah,
So no,
Wiggles
in
wobble.
general, we don't put magnets on satellites.
Okay, that's a good thing. I mean, there's a question directed at you, and I'm not sure you have the power to answer this, but or to control this. But with the huge proliferation of satellite launches, for example, Starlink, how do you intend to regulate the process of getting companies to seek permission to launch new satellites? I mean, I guess how does the space industry or the space agencies, I guess?
Well,
Um,
I mentioned the problem of space law, and space law as if very much the Wild West right now. Um, Essentially, you can put whatever you want up there if you follow a modicum of regulations like don't damage other people's stuff.
yeah,
Now, that's not going to cut it, obviously, because people have been doing exactly that, and that's what's gotten us to the situation we have. So there is a lot of research currently on space law and litigation and the responsibilities of countries to be able to have a shared use of space. At the moment, it's kind of like international waters. So we have this idea of international waters not owned by any country, but you have to have some sort of responsibility of care for the space that is shared by all different countries. We need to have that responsibility of care enshrined in with all of the spacefaring nations in their regulations, because in the end, it has to be the individual nations who impose upon and who specifically regulate the use of space for their industries. I don't think you're going to see a global space management board pop up because I don't think countries would stand for that. So it's going to be again, it's going to be cooperation, and it's going to be the advancement of the structure that we impose upon the use of space.
Excellent. I've got an interesting question about powering satellites. For near-Earth operations, solar arrays will be fine, but what about deep space environments that reach out with diminishing solar energy availability? Very smart question.
Yes, well, if you look at most of the deep space missions, for example, missions to Pluto and so on, they use what's called a radioisotope thermoelectric generator, or RTG. And basically, what that is a big lump of radioactive material. And as it decays, it produces heat. And you put some thermocouples or things like Peltier junctions, which are two metals, and you heat it up and it produces an electric potential. You put these around that radioisotope, and it will produce a certain amount of electricity continuously just because of radioactive decay. Now, over time, that radioactivity will decrease. So if you look at, for example, the Voyager 1 and Voyager 2, Voyager 1's already left our solar system. It's at the heliopause. Its RTG is producing a fraction of the amount of power it did originally. It's still going, but RTGs are not permanent. You can think of it as kind of like a really long-lived battery. So if you can't get enough light from a solar panel, really, I think that's the only other big option we have right now. Power is an issue. Until we have reproducible net positive nuclear fusion, the RTG is still the best solution, I believe.
Well, at York, we're working on it. We're trying to help you guys with it.
Indeed, yes. And we very much appreciate the Department of Physics working on these problems.
Exactly. It's a big, big piece of nuclear fusion. And that's one of the things that we talk about. It's the ability for it to potentially be operational in space, which is an interesting application. A few more here. In the early side, you had some slide, you had something like 900,000 objects caused by explosions from residual fuel in rocket stages from 1961 to 2020. Does that mean that this source of debris has now been stopped? And if so, how?
The rocket bodies situation, for example, has been mitigated to some degree. You may notice Blue Origin, SpaceX, for example. One thing that they are doing is they have reusable boosters. So their lower stages generally come back to Earth. They've got a bit of fuel left in them. They land them, clean them up, reuse them again.
Nice.
Uh, I don't think we're reusing upper stages yet. That is the part that actually goes all the way up to deliver the payload. However, launches now are planned in such a way that those payloads will decay in their orbit. They will hit atomic oxygen and nitrogen in the upper atmosphere, and they will gradually fall back to Earth, preferably in the middle of the Pacific Ocean where there's nobody else for it to fall on. But that's all planned out now. In the past, that was not planned usually for two reasons. First of all, they didn't have the technology then to precisely control where things fell. The second reason was they put a lot of things up in much higher orbits. So when you put things into a higher orbit, it's harder to get the thing that sent it into a higher orbit back down to Earth. I don't believe that's done consistently now. No, I think for things like geostationary orbit, which is quite far from the planet, we are still putting stuff up there occasionally. Usually it's put into a graveyard orbit close to geostationary orbit where it won't collide with any satellites, where it will be out of the way and not cause trouble. But we are still adding to the problem. So we haven't completely closed off that yet. We've only sort of decreased the amount of rubbish that we're producing.
Yeah. And apparently there was a noticeable dip somewhere before 2000. Can't remember the exact year. Well, they've got a questioner asking, was there a reason for that?
Noticeable dip in space junk or in launches.
In I think it was in objects in space, space junk.
Yes, an object. So yeah, there was a dip. I see. There was a dip around 1990,
That might be
but
it.
that was mainly because there were less launches around then. There were less things being put into space and more things being deorbited. It's not as though we never deorbit things. If
Yeah.
you leave something in low Earth orbit long enough, it will eventually slow
Burn.
down and fall
Yeah.
back to Earth. The problem is that there's now a net gain as opposed to a net
Yeah.
decrease. So there have been a couple of times when the total amount of debris has decreased, yes.
So if we did nothing and they didn't hit each other, it would gradually decay down
If
because
we
they would
did
eventually
nothing,
lose.
if we did nothing in 1990, the situation may have stabilized.
Right.
Yes. But I don't think it will
Mm.
stabilize now, is the problem.
And then how would yeah, it's an interesting question because well, it uses the word laser, and as a laser plasma physicist, of course, if it's got the word laser in it, I'm sold.
Yeah.
Why would we use a laser to destroy the debris? Won't it create more small debris?
Yes, if we used a laser to destroy it, that is to explode it, yes, that would be the case. However, with those lasers that I mentioned, they exert a pressure, in fact, a photonic pressure on the debris. Remember, this
Mm.
isn't for big objects. This is for tiny, tiny objects,
Yep.
1 centimeter, maybe 2 centimeter size. Now, you might not think that light applies a pressure, but actually it does. There is an energy transfer when you focus photon beam on something. You're actually transferring momentum to the object. And we've proven this. We've tested actually that photons work as a momentum source because we've put up satellites that are what we call solar sails. And these solar sails, you open them up and you actually can catch sunlight, and the sunlight gives you a little bit of a push.
Yep.
You can look that up actually. Solar sails are a thing. They've actually been tested and worked. So the laser is basically the same idea, but much smaller area.
Yep. And the power is proportional to the intensity over the speed of light. And
Yes,
this is
exactly.
something I taught this in a lecture yesterday on fusion energy because when you think of a fusion capsule being compressed, it's not the same physics because the light pressure is not enough actually. It's an ablation pressure, which also could work, but you need a really intense laser and you'll never get it that far into space. The other one, oh, how much orbit can a star fab effectively cover? In other words, how many star fabs will we need in order to solve this problem?
That's a really good question, actually, and that's one we haven't completely solved yet. You see, to be totally transparent about it, there are still issues with the StarFab hub, and the issues are not with whether we can put up a space warehouse. The issues are getting things to the hub. So I talked about how capturing things in orbit is very difficult, and if you get it wrong, you make the problem worse. So even if you're capturing cooperative targets, you have to get that space tug all the way over to your target, which could be thousands of kilometers potentially, and all the way back. It takes time, it takes fuel, and there's only a certain number of satellites you can service, with that amount of fuel and with the amount of time that you have. Now, we've run the numbers, initial simulations, and so on. And in low Earth orbit, I mean, we probably only need one or two star fabs because we don't need to cover that much area. And things in low Earth orbit tend to move really quick. So if we grab them at the right time, we can pull them over to StarFab and service them. Now, if you're talking about things like geostationary orbit, which is much further away, it's a big challenge, in fact, getting things all the way there and all the way back. I don't know how many StarFabs we would need, but we would certainly have to improve the technology we use to get things around in orbit. So maybe we'd have one StarFab just dedicated to geostationary orbit, and we'd have to somehow make it move because things in geostationary orbit, they're there because they rotate at the same speed as everything else. So yeah, there are still issues. There are still operational challenges, I would say, with that.
Yeah. There's a very quick, I guess I hope it's a quick answer in that if you can get common docking architectures and commonality between the way different countries are doing it, would that have helped the recent incident with the Chinese astronauts having their spacecraft damaged? Would it have been possible for other countries to rescue them if there was common interoperable architectures were agreed to? And is that being pursued?
That is definitely being pursued. The challenge is not so much technology, the challenge is common agreement. Now, China has gone very far ahead in terms of technology. They've developed wonderful systems, but they haven't shared them as much with the rest of the world as we'd like to see. So yeah, I mean, in the case, for example, where a SpaceX capsule would have to rescue a Chinese capsule, for example, or dock with the Chinese space station, I'm not sure they could do it right now. There was a mission called Apollo-Soyuz, which was the first docking between the Soyuz Russian spacecraft and the Apollo American spacecraft, just to prove that it could be done. But they had to make a lot of custom hardware for that to work. They had to make a custom docking adapter. They had to have special protocols, special communications. And it's very much the same today. I'm sorry to say it. It hasn't
Yeah.
really made it much easier. So yes, we definitely need to talk more. We definitely need to standardize.
It's the story of the world in general. Well, well, I mean, we've slightly overrun. I apologize for that, but we've gone over by about a minute. But I mean, it's clear that not only are you incredibly knowledgeable and enthusiastic about your topic, but you're explaining it beautifully to all of us who are listening, myself included. So, thank you so much for your contribution to the webinar series this evening.